In the last few sections, we've talked about how to find derivatives, and we've looked at how to evaluate the derivative at a point. First, we looked at how to find f prime of a, and then we looked at how to find the actual derivative as a function, f prime of x. But both of these two have relied on that limit definition, limit as h approaches 0, f of x plus h minus f of x, all divided by h. And if we're going to be talking about derivatives for about half of this class, it would be, I'm sure you're all thinking, boy, it would be really nice didn't have to use this every single time. Like, great, that's real cool, Mr. Huber. Derivative tells us some awesome stuff, but come on, there's got to be a way. Show me the shortcut, and you know what? Say no more, fam. I've got you covered. So we're going to talk about in this section how we can speed up and make the process of finding the derivative a whole lot easier. So the first shortcut we're going to learn, really nice, says if c is a real number, then the derivative, remember this says the derivative of c is simply 0. And to understand kind of why this is, I'm just going to draw in a constant function. So let's say I chose y equals 3, just for the sake of picking a number. So here's y equals 3. Remember that the derivative tells you the slope of the tangent line. So if I pick, let's say, this point right here, and I drew in the tangent line, it would look something like this. Well, the slope of that red line is 0. Everywhere. So the derivative must be 0. And that's not a unique occurrence. If I pick, say, this x value over here, sketching the tangent line, it's kind of silly to think about, but that tangent line is just going to fall right on top of it. What's the slope of that tangent line? Well, it's 0 once again. You could pick any x value you want. If I pick 0, right? I'm not smart, Mr. Huber. If I draw in the tangent line, what's the slope of that tangent line? Well, my graph isn't particularly perfect, but if it were, you'd say, well, the slope of that tangent line is 0. So the derivative must be 0. And this works for any function, or any constant, excuse me, as long as you're just dealing with a constant. So if your y equals 3, then we can say with absolute certainty, if your y is equal to 3, then y prime, the derivative of that, is equal to 0. Doesn't matter what constant it is. You could say, okay, I'm going to say y equals pi, right? Pi is a constant, 3.14159 something or other. It's just a constant, 3.14 blah, blah, blah. Derivative of any constant is 0. So any constant you can imagine, even 0, right? Sometimes I think, okay, what about y equals 0? 0 is a constant, so the derivative of 0 is just 0. So, okay. That's really nice. If we have any constant, I know that the derivative of that constant is equal to 0. So now we're going to see if we can come up with a better way to deal with functions that are more complicated than just constants. Because, okay, it's cool that we have this really handy shortcut for dealing with constants, but most functions we work with are more complicated than that. So what I'm going to do is I'm going to start with what's the next most complicated function I can think of. I think of f of x equals x. What I'm going to do is I'm going to work through the limit definition of the derivative for this function. I'm going to do that for this function, and then I'm going to work one more, x squared. I'm going to see if I can start to identify some sort of a pattern here. So if I start with f of x, remember we're using the limit definition here, so we will be using limit as h approaches 0, f of x plus h minus f of x divided by h. I'm going to speed through this process pretty quick here. So first step 1, f of x plus h. This is kind of silly to think about because it's just x plus h. I can't do anything with that. 2, if I subtract my original function, I'll have x plus h minus my original function of x. Well, hold on, those two cancel, and I'm just left with h then. Okay. Step 3 right here, I'm going to take what I found in step 2, divide it by h, right? That's this piece over here, divided by h. H divided by h, that's just 1. Okay, well, step 4, I'm going to take the limit then. Limit as h approaches 0 of what I found at the end of step 3. That's just 1, so that's just 1. This is my derivative, f prime of x. So if f of x equals x, I just found the derivative of that function is equal to 1. So okay, that's pretty cool. That was a nice little one to work with. So I say, okay, I have f of x equals x. What's the next most complicated function I can think of? Well, what if I had g of x equals x squared, right? I just kind of bump the exponent up by 1. Let's see if we can work with that. Do the same process here with x squared now. So step 1, g of x plus h would be x plus h quantity squared. You will have to FOIL that out. So that really says x plus h times x plus h. We'll end up with x squared plus 2xh plus h squared. Step 2, I want to subtract my original function. So I want to take what I just found, x squared plus 2xh plus h squared, minus my original function. Well, that's just x squared, so minus x squared. Well, my x squared terms cancel. I'm left with just 2xh plus h squared. Okay, step 3. Step 3 says, okay, we take what we just found, 2xh plus h squared divided by h. And here, let's see, in my numerator, I can factor out an h. That leaves me with 2x plus h divided by h, and then my h's will cancel. That's exactly what I wanted. Step 4, okay, let's go ahead and take the limit as h approaches 0. What was I left over with in step 3? I had 2x plus h. So I'm just plugging 0 in for h. This is 2x plus 0, which is just 2x. So that's my derivative g prime of x. So if I start with x squared, I ended up with g prime of x is equal to 2x. Okay. But okay, well, what's the next most complicated function I can think of? Well, we've been bumping the exponent up by 1. Let's do that again. I'm not going to make us do this problem because, to be honest, once we start working with exponents higher than 2, the algebra gets a little bit obnoxious. Because your first step would be, let's go find x plus h times x plus h times x plus h. And I don't really want to do that. It's kind of long and tedious, and I think we'll get kind of a similar idea here. Is if I just tell you, okay, if I start with h of x equals x cubed, the derivative of that function is 3x squared. If I bump that exponent up one more time, y equals x to the 4th, hopefully we can look at this and start to make an educated guess. Y prime, the derivative of that, will be 4x to the 3rd power. So let's think about this here. Let's maybe try and organize this information just so that it's all in one spot. We said, okay, if y equals x, the derivative of that is 1. If y equals x squared, the derivative of that is 2x. If y equals x cubed, the derivative of that is 3x squared. If y is equal to x to the 4th, y prime is equal to 4x cubed. Hopefully we're seeing a pattern, particularly with these last 3. The first one is a little bit difficult to see. With these last 3, hopefully we say, okay, how can I get from y to y prime? What's going on there every single time? Well, something's going on with this exponent, right? This exponent every single time, so if I look at, let's say, 3 here, started with 3, then I have 3 as a coefficient. And then I look, okay, well, what happens to my exponent? My exponent changes. It goes down to a 2. 4 right here, that becomes my coefficient, and my exponent gets bumped down to a 3. So hopefully we're starting to see this pattern here, and this pattern is not purely a coincidence, luckily for us. It is the power rule. So this says if n is a non-negative integer, so right now we're going to work with only positive integers here, or 0, I suppose. 0 would work as well. Then the derivative of x to the nth is n times x to the n minus 1. So this is a really, really nice rule that we're going to be using a lot here. The power rule essentially says when you're dealing with a non-negative integer, you can break the derivative down into 2 steps. First, what do we do with this n? Well, we multiply by that n. So we multiply by the power, multiply by the power of your variable. 2, what do we do with that power then? Well, we take that power, we subtract it by 1. So we subtract 1 from the power. So let's see if we can apply this here just to kind of find some simpler derivatives. Part A, here this says find the derivative of x to the 8th. So if I want to find the derivative, I would multiply by my power, multiply by 8x, subtract 1 from my power, I would have x to the 7th power. There's my derivative. Didn't have to go use that long limit definition, break it up into 4 steps. Nope, I just multiply by the power, subtract 1 from the power. It's really, really nice. Here I have the derivative of x to the 10th. So, okay, I multiply by my power, 10x, and I subtract 1 from my power. So 10x to the 9th power. That's it. There's my derivative. Look at this. This is going so smoothly. Derivative of x to the 28th power. So, okay, multiply by my power, 28x, and then I subtract 1 from my power to now to the 27th power. That's it. There's my derivative. What derivative of 4 to the 7th? This is a trick question. I'll tell you right now. Notice that this isn't x to the 7th, this is 4 to the 7th. I could actually go and figure out what this is. This would be 4 times 4 times 4 times 4 times 4 times 4 times 4. And I could go figure out what that number is. It'd be obnoxiously large, but what is that number? This is a constant. Be careful. This is a constant. What's the derivative of a constant? Derivative of any constant, we said earlier, 0 every single time. So please, please, please be very careful. This is something that will pop up from time to time. This will be a trick question you'll see every now and then. If you have a constant raised to a power, derivative of that is always going to be 0. It's only if we have our variable raised to some power, so x to some power, or t raised to some power, that we're going to be using this power rule. One other thing I just want to make a quick note of, there might be one of these examples. This one I think kind of stands out as, well, doesn't really look like it fits the power rule. It might look a little bit different, and I just want to talk about why. Our function is really y equals x to the first power. And if we apply our power rule, y prime is equal to, I multiply by my power 1, x, and then I subtract 1 from my power, I have x to the 0th power. Remember that anything to the 0 power is simply just 1. So 1 times 1, which is 1. So it actually is the power rule. We just have that exponent of 0 that kind of, I don't want to say gets rid of our variable, but we'll say makes it disappear, I suppose. So this is a really, really nice rule, a really nice theorem. It speeds up our process of finding derivatives a whole bunch. Let's talk about a couple others that we have here. The next one is the constant multiple rule. It says if f is differentiable at x and c is some constant, then the derivative of c times f of x is c times f prime of x. So, okay, great. That's a lot of math jargon. Can you just tell me what that means? Sure. This essentially just means that a constant multiple is not going to have a drastic impact. So, when I look at this example right here, derivative of 4x squared. if I want to look at the derivative of 4x squared. Really what this is saying is you can almost just factor this 4 out. You can say, okay, well this is actually just 4 times the derivative of x squared. So this is 4 times, what's the derivative of x squared? Use our power rule. 2x, subtract 1 from my power, this is 2x to the first. 4 times 2, I have 8x. So really what we're doing is we're factoring this constant multiple of 4 out, and then we're multiplying it by the derivative. Now this is, I think, a little bit more complicated than it needs to be. I don't need to see this level of work. The constant multiple rule, I think, also kind of, what's the word I'm looking for here? It appears in a very intuitive way. So if you said, hey, take the derivative of 4x squared, if you just kind of wanted to extend the power rule to include constant multiples, the power rule says, okay, I multiply by my power, so really I have 4 times 2, and then I subtract 1 from my power. 4 times 2 times x to the first would be 8x. So a lot of us would just say, all right, this is just 8x, and I could even just jump to saying 8x if I wanted to. I don't necessarily need to show this step, but that's really what's going on here. Next up, I've got f of x equals 4/5 times the square root of x. Square root of x is actually, we said the power rule works for non-negative integers, and if we're working with square root of x, that's actually x to the 1/2 power. It's not a non-negative integer. So we're going to give the hint right here. We're going to just say that, hey, if you want to take the derivative of square root of x, it's really just 1 over 2 square root of x. And it will justify that later on. Don't worry. We'll come back to that and talk about why that is, the way it is. Why it looks maybe a little bit different. So if I take the derivative f prime of x, this 4/5 kind of just comes along, 4/5. I'm going to multiply it by the derivative of square root of x. Well, square root of x, derivative of that guy is 1 over 2x. So times 1 over 2 radical x. From there, I just need to simplify this a little bit. So let's see, 4 times 1, I've got 4 over 10 square root of x. I can simplify that. This is 2 over 5 radical x. There's my derivative f prime of x. So we just multiply the derivative by that same constant multiple that appeared in our original function. G, same idea here. So G, if I want to find G prime of x, this negative 6 over 11 doesn't really have a big impact. Let's just say negative 6 over 11 times the derivative of x to the 10th. Well, that's 10x to the 9th power. And at this point, if I wanted to, I could say, okay, this is over 1. Negative 6 times 10, I've got negative 60x to the 9th power divided by 11. Here's my derivative. We also could have just said, hey, 10 times negative 6 over 11, that's where we would have gotten negative 60 over 11 from. So constant multiples really not going to dramatically impact the way that we find derivatives, which is really, really nice. So we're going to continue this thought process in the next video. We're going to continue to extend, okay, what happens if we're adding and subtracting? What happens if we're multiplying and dividing? We're just going to keep trying to build on this power rule and see where it stops.